Hello, I'm gonna present my final project of this course. The topic is build an agent with better performance in unseen levels of Sonic the Hedgehog games. Okay, so I will start with some motivations. First, reinforcement learning algorithm has achieved notable success recent years in goal-oriented tasks like the Go game. The algorithm even can beat the human being expert. And it's commonly known that the RL algorithm performs well when given a good reward function and only unlimited time to interact with the target environment. But it's not always the case in practical setting. And we expect model to utilize prior knowledges to acquire new skills in unseen environments more quickly, just like the common learning process in human beings. And also with the progress from transfer learning domain, RL algorithm can be modified to speed up learning rate and still maintain a relatively good performance across different tasks. Okay, so this whole problem belongs to this meta learning setting. So in the first step, you train a meta learner on multiple training levels, and then you have a trained model. Use this trained model as a starting point on some unseen test levels, and you train fine tune the parameters of this pre-trained model to tailor for your new task levels. Okay, so the the package I'm using for this project is called Gym Virtual Environment. So it's a wrapper for video game emulators. Using this API to run them into gym environments, it can support several classic uh, game consoles and it contains a database of a bunch of different games, video games. What you can test the various reinforcement learning algorithm or frameworks using this virtual environment. The dataset I'm using contains 58 levels from these three different video games. Basically, the Sonic the Hedgehog 2nd, and the Sonic 3 and Knuckles. These are the screenshots of these three video games. So the general goal is that this agent needs to start from the left of the map and find a path uh, to go to the right end of the map, and the time the completion time uh, the agent will get more reward if it can complete the whole process in a shorter time. Okay, so these are two baseline methods I implemented during the process. The first is called jerk, just enough return knowledge. This algorithm completely ignores observations and instead just look at rewards. Uh, it's it's not a deep learning. It's not a deep learning model, but it can sometimes achieve high rewards on the benchmark. So the main idea is to explore using a simple strategy, like going right for several steps and jump at some point with some probability, and then to replay the best action sequence more and more frequently as training progresses. Another method is called PBO, or proximal policy optimization. So it's a new family of policy grading method for RL, which alternate between sampling data through interaction with the environment and optimizing a surrogate objective function using stochastic gradient ascent. So this PPO have uh, can have the same benefits of this trust region policy optimization, but it's much easier to implement. So for these two methods, I trained a separate model for each game level. Okay, so uh, a more advanced model is called I tried is called a joint PPO model. So this model applies this uh, meta learning procedure. First, you have first see if you have n training levels, and you have m parallel workers. Each worker explores one level of the game for some t time steps, and at every gradient update step, all workers average their gradient together to do the gradient update. Later on, finally, after these t time steps, you will get a jointly trained model. The second step is that you use this joint trained model as a starting point uh, for the new test level, which hasn't been seen in the training process. And the rest hyperparameters are the same, and the training process are the same as training a single PPO model. All right. So this is the results. This is the first column is algorithm. The second column is average. Is an average score across multiple testing levels. We can see that this jerk algorithm has a worse performance. But this joint people model significantly improves the rewards agent can get. And also, mm, this deviation from the mean increases from the simple model to more complicated model. I think may, the reason may be that this jerk model tend to tends to learn similar path across uh, different runnings. But this joint PPO model can learn more diverse paths from the left to the right of the map. So, like I said, I use the pre-trained joint model as a starting point for new test level. So it could be possible that you have overfitting model on all these training levels. So I sampled checkpoints along different at different time steps, from 2 million to 200 million steps. So we can see from this figure, the x-axis is a time step you fine tune the model on new test level, and the y-axis is the mean reward score you achieved. We see that uh, without pre-trained model, the performance is the worst. Uh, and with the increasing of these time steps from 2 million to 20 million steps, we can see the increasing of the performance. But after these 20 million steps, all all these the performance is similar across different sample checkpoints. So I use this 20 million step checkpoint for the later on fine tuning process.